Mechanical engineering means having expertise in applying various concepts, skills, and tools. So, based on different subfields, one should have knowledge, skills, and expertise in the following areas in today's time. Key fundamental concepts in mechanical engineering, along with the skills, techniques, and hands-on tools that enable engineers to apply these concepts effectively in problem solving. Mechanics, including statics and dynamics, is fundamental. Statics involves the study of forces, moments, and equilibrium in systems that are at rest or move at a constant velocity. Dynamics, on the other hand, focuses on the study of forces and torques and their effect on motion. Skills and techniques in this area include using free body diagrams to visualize forces, moments, and resulting reactions on a body. Mathematical modeling involves using equations of motion, such as Newton's laws, to predict the behavior of mechanical systems. Simulation tools like MATLAB or Simulink are also essential for dynamic analysis. Hands-on tools include force sensors for measuring applied forces in experimental setups and motion capture systems for analyzing the movement of objects in dynamic studies. Thermodynamics is another crucial area. The first law of thermodynamics deals with the conservation of energy within a system. The second law of thermodynamics introduces the concept of entropy and the direction of natural processes. Heat transfer, including conduction, convection, and radiation, is also a key concept. Skills and techniques here involve formulating and solving energy balance equations for energy conservation, using heat transfer analysis techniques like Fourier's law for conduction, and analyzing thermodynamic cycles such as the Rankine cycle or Carnot cycle. Hands-on tools include thermocouples and infrared thermometers for measuring temperature changes, and heat exchangers used in labs for studying heat transfer. Fluid mechanics is essential too. The continuity equation deals with the conservation of mass in fluid flow. Bernoulli's equation relates pressure, velocity, and elevation in fluid flow. The Navier-Stokes equations are the governing equations for fluid motion. Skills and techniques include dimensional analysis to simplify complex fluid flow problems using dimensionless numbers like the Reynolds number. Computational fluid dynamics, or CFD, uses software like ANSYS Fluent or OpenFOAM for simulating fluid flow. Piping and duct design involves calculating pressure drops, flow rates, and selecting appropriate pump or fan sizes. Hands-on tools in fluid mechanics include wind tunnels for experimental analysis of fluid flow over objects and flow meters for measuring the rate of fluid flow in pipes. Materials science. Key concepts. Stress-strain relationships, understanding the deformation and failure of materials under load. Fatigue and fracture mechanics, behavior of materials under cyclic loading and crack propagation. Phase diagrams, understanding the microstructure and properties of materials. Skills and techniques, material selection, choosing appropriate materials based on mechanical properties, cost, and performance criteria. Failure analysis, techniques like fracture surface examination to determine the cause of failure. Heat treatment processes, understanding and applying processes like annealing, quenching, and tempering to modify material properties. Hands-on tools. Universal testing machines for testing material strength, elasticity, and other properties. Microscopes, both optical and electron, for examining microstructures and fractures. Machine design. Key concepts. Load analysis, determining the forces acting on machine components. Fatigue analysis, assessing the durability of components under repetitive loading. Kinematics of machinery, study of motion in mechanisms without considering forces. Skills and techniques. CAD, using tools like SolidWorks, AutoCAD, or CATIA for designing machine components and assemblies. Finite element analysis, using software like ANSYS or Abacus for stress analysis and optimization. Tolerance and fits, applying geometric dimensioning and tolerancing in mechanical design. Hands-on tools. Three-dimensional printers for prototyping and testing design concepts. CNC machines for precise machining of components. Control systems. Key concepts. Feedback and control theory. Systems that regulate themselves through feedback loops. Transfer functions. Mathematical representation of a system's output in relation to input. Stability analysis. Determining the conditions under which a system remains stable. Skills and techniques. PID control. Tuning proportional integral derivative controllers for system stability. Mathematical modeling of dynamic systems, using differential equations and Laplace transforms. Simulation using software like MATLAB or Simulink for designing and testing control systems. Hands-on tools. oscilloscopes for visualizing electrical signals and system responses, control system kits, educational kits for hands-on learning of control system concepts.